Today we are going to discuss about kinetic isotope effect, Hammett equation and linear free energy relationship. We are going to see what is kinetic isotope effect. Substituting one isotope for another or near an atom at which bond breaking or rehybridizing typically leads to a change in rate of the reaction. This phenomena is called kinetic isotope effect. Isotopic substitution has no effect on the chemical reactivity of the substrate, but it has an noticeable effect on the rate of the reaction. Kinetic isotope effect are used to determine reaction mechanism by determining the rate determining step of multi-step process, and we get an information about the structure of the transition state in the reaction. The kinetic isotope effect is measured as the ratio of rate of two different labeled isotopic molecule in a chemical reaction. Primary and secondary isotope effects are represented as the ratio of rates for the light isotope to the heavy isotope, that is kinetic isotope effect equal to Kh by Kd. On comparing this, we get Kh by Kd is equal to 7.8 at 25 degrees Celsius. The rate of reaction involving CH bond is 6 to 8 times more faster than when it is replaced by a CD bond. But in case of C20, the reaction rate is approximately equal to 1.04 times faster than when it is replaced by C13 molecule. Isotope rate changes are more pronounced when the relative mass is greatest. The magnitude of kinetic isotope effect is used to elucidate the reaction mechanism. There are different types of kinetic isotope effects. First one is primary kinetic isotope effects. These are the effects when there is a rate change due to isotopic substitution at the site where bond breaking takes place in the rate determining step. The value of Kh by Kd will be 7 in the case of primary kinetic isotope effect. Second one is secondary isotopic effect. Secondary isotopic effect is defined as the effect where there will be no bond breaking in the isotopically substituted atom. This effect is smaller compared to the primary kinetic isotope effect. In the case of secondary kinetic isotope effect, the Kh by Kd value will be smaller than 1. The reaction rate will be lower for hydrogen when it is replaced by deuterium. Reaction where the deuterated species reacts more faster than the undeuteriated species. This reaction will be inverse kinetic isotope effect. There will be two types of secondary kinetic isotope effect. First one is beta secondary kinetic isotope effect. Isotopic substitution in the beta position where bond breaking takes place in the rate determining step. We have two reactions. In the first reaction, there will be initial elimination of this X to form a carbocation. Then there will be the attack of nucleophile to form this product. In the second reaction, there will be also the elimination of X in the initial step. Then there will be the formation of a carbocation, and there will be the nucleophilic attack to this carbocation to form this product. In both the steps, the formation of carbocation takes place without the breaking of bond having isotopic substitution. Here there will be hydrogen in the beta position and there will be deuterium in the beta position. Deuterium will be less stable than hydrogen. As the stability increases, the rate of formation of product through that pathway will also increases. Thus, Kh by Kd will be greater than 1. The rate of beta secondary kinetic isotope effect is caused by beta substituent. Then we have alpha secondary kinetic effect. Isotopic substitution at the alpha position when bond is broken in the rate determining step. Normally there will be a change in hybridization in alpha secondary kinetic effect. That is, there will be a change in sp3 to sp2 hybridization. Then we are going to discuss about Hammett equation, its significance and applications. Hammett equation is a general equation which relates quantitatively structure to rate constant or equilibrium constant. Hammett sets up an equation that is log k by k0 equal to sigma into rho, where k is the rate constant or equilibrium constant for substituted phenyl compounds. K0 refers to the same reaction for unsubstituted phenyl compounds. If we take ionization of benzoic acid as an example, K0 is the ionization constant for substituted benzoic acid and K0 is the ionization constant for unsubstituted benzoic acid. Then we have the term sigma. Sigma is the substituent constant, that is which indicating electron withdrawing and electron releasing groups. That is the effect of substituent on rate of reaction. Then we have the term rho. Rho is the reaction constant, that is for a particular reaction for a given set of reaction conditions. Rho value was set up to 1 for substituted and unsubstituted benzoic acid in water at 25 degrees Celsius. Then if the value of rho is equal to 1, then we can find out the value of sigma. That is sigma equal to log K C6H4COOH to log K0 C6H4COOH. That is we take the ionization of benzoic acid as an example to calculate the value of sigma. Here rho is equal to 1. Then we get this equation. Sigma is the effect of substituent on a rate of a reaction. Sigma value is different for meta to para positions. Then we are going to see what is substituent constant. That is sigma. Sigma is a number. Since sigma is determined by taking logarithm of ionization constant of substituted benzoic acid to logarithm of ionization constant of unsubstituted benzoic acid. Sigma is a measure of total polar effect, that is the ability of substituent to withdraw or electron or release electron by the combination of inductive or resonance effect of the substituent. The sigma value may be a negative or a positive number. Sigma value varies for the same substituent if it is in meta position or it is in para position. Then we are going to see what is substituent constant. Sigma is a number. Since sigma is determined by taking the logarithm of ionization constant of substituted benzoic acid to ionization constant of unsubstituted benzoic acid. Sigma value for hydrogen is taken as 0. Sigma value is a measure of total polar effect, that is the effect of substituent to withdraw or release electron by the combination of inductive and resonance effect. Sigma value may be a positive or a negative number. sigma value for a particular substituent varies from meta to para position. Then we are going to see an example, that is KC6H5COOH and meta-methoxybenzoic acid. The K value, that is the ionization for benzoic acid, is 6.3 and for meta-methoxybenzoic acid is 8.3 into 10 raised to minus 5. Delta value may be a negative or a positive number. A negative sigma value indicates that the substituent has a greater electron donating ability to the reaction center than hydrogen, whereas a positive sigma value indicates its electron withdrawing character. In the case of benzoic acid, its value is 6.3 into 10 raised to minus 5, and in case of meta-methoxybenzoic acid, the ionization constant value is 8.3 into 10 raised to minus 5. Hence, we can conclude that meta-methoxybenzoic acid has greater electron withdrawing ability than benzoic acid. Then we are going to see what is a reaction constant, that is rho. Reaction constant, it indicates the need of a reaction to withdraw or release electron. Rho value may be a negative or a positive value. A negative rho value indicates a larger electron demand at the reaction center, so that an electron donating group accelerates that reaction. A positive rho value indicates a negative transition state, so that a electron withdrawing group accelerates those reactions. Then we are going to see the applications of Hammett equation. In the Hammett equation, we have 4 measurable quantities, that is K, K0, sigma and rho. If any of the 3 quantities are known, we can find out the 4th quantity. The second application is to compare the acidity of acids quantitatively. Then we are going to discuss linear free energy relationship. Hammett equation is a linear free energy relationship. This can be demonstrated by taking into consideration the dissociation constant of substituted and unsubstituted benzoic acid. For substituted benzoic acid, delta G0 is equal to minus RT ln Ka, and for unsubstituted benzoic acid, delta G00 equal to minus RT ln Ka0. Thus, the Hammett equation can be written as, by taking the value of ln Ka from this equation and ln Ka0 from this equation, Hammett equation can be written as log Ka minus log Ka0 equal to sigma into rho. When we rearrange this equation and convert ln K in terms of logarithm, we can get this equation, that is minus delta G0 by 2.303 RT plus delta G00 by 2.303 RT equal to sigma into rho. These two denominators are same. When we take LCM and cross multiplying this, we get the value of delta G0 as sigma rho 2.303 RT minus delta G00. For a given reaction, under a given set of reaction conditions, R, T, delta G00 are all constants, then the value of sigma varies linearly with delta G0. Just as standard free energy changes are proportional to equilibrium constant, standard free energy change of activation is also proportional to rate constant. Then we are going to see delta G0 equal to delta H0 minus T delta S0, and at standard conditions delta G0 star equal to equal to delta H0 star minus T delta S0 star. It was initially believed that the electronic effect of substituents principally affects the enthalpy change. Then we get Hammett equation as a linear plot because the enthalpy change caused by substituents are either small or parallel enthalpy changes. It can be demonstrated as a easy case, but the actual facts are more complicated.